Okay, hopefully you've had time to work out these solutions here. And so we can compare results on our answers now. For the first one, we've got 65 centimeters. Centi means 10 to the minus 2. I probably should have left a little more room on these. So 65 times 10 to the minus 2, 65.0. You want to maintain the number of significant figures. That 0 at the end is significant because there's a decimal point. So that means this is 3 significant figures. So your answer should also be 3 significant figures. So it's 65.0 times 10 to the minus 2 meters. Now the question is whether that's proper scientific notation or not. And actually it's not, because as you'll notice, this first number here is 65. That's not between 1 and 10. So we have to move the decimal point in a direction that makes the number between 1 and 10, which makes it 6.50. Remember, you have to keep that 0 at the end because it is significant. And so you end up with 6.50 times 10. The power of 10 now is, since we made the number smaller by moving the decimal point, you have to make the negative 2 bigger by 1. And remember, with negative numbers, negative 1 is bigger than negative 2. Okay, so that's 6.5 times 10 to the minus 1 meters. That would be the same measurement in proper scientific notation. Okay? Okay, 95 kilometers. Kilo means 10 to the third. Ooh, I don't know if you can even see that, but 10 to the third. So 95 kilometers would be 95 times 10 to the third meters. This is not proper scientific notation, though, because it's not between, the first part of the number anyway, is not between 1 and 10. So we take our decimal point, we have to draw it in since it wasn't there already, and move it in a direction that makes the number between 1 and 10. That would be the left. So this becomes 9.5 times 10, and moving the decimal point made the number smaller, so we have to make the exponent bigger to compensate. So that would be 4. 9.5 times 10 to the 4th meters would be the same as 95 kilometers. And this is in proper scientific notation. 1.5 decimeters. Remember, decimeters would be 0.1 or 10 to the minus 1 of a meter. 1.5 of them would be 1.5 times 10 to the minus 1 meters. And actually, that is proper scientific notation because 1.5 is obviously between 1 and 10. So there you go. The next measurement, 2.8 gigahertz. As I said, hertz may be something you may or may not have ever heard of before, and you may or may not know what it means. But it's a metric unit. That's all you really need to know now. But giga is the part that we're interested in here. Giga means 10 to the 9th, or a billion of something. And so 2.8 gigahertz would be 2.8 times 10 to the 9th of the base unit, which is hertz, or Hz. And this actually is proper scientific notation. As an aside, what hertz means it's a way of measuring the frequency of electromagnetic radiation. And electromagnetic radiation is just basically energy that travels in the form of waves. And there's a wide variety of stuff that counts as electromagnetic radiation, like radio waves, TV waves, microwaves, infrared, ultraviolet, visible light, X-rays, all kinds of things like that. They travel in waves, kind of like that. It's a little badly drawn, but anyway. One wave is considered to be from the peak of one wave to the peak of the next, so that would be considered one wave. And they all travel at the speed of light, but the actual distance between waves can change for different types of electromagnetic radiation. And so when we measure the frequency, we measure how many waves can pass a given point per second, and that would be the frequency in hertz. A lot of these waves are really, really short, so you can fit an enormous number of them past a given spot every second. And in this case, 2.8 gigahertz would be 2.8 billion waves per second passing any given point in space. So that is a really high frequency. Anyway, that's just kind of like a background of what hertz means. If you look at a radio dial, I mean, you know, one of the old-fashioned radios that actually has a dial on it, you can see that AM radio is marked off in units of kilohertz, which means thousands of waves per second, and FM is marked off in megahertz, or MHz, which is millions of waves per second. So you may hear WNED in the background. That's 94.5 megahertz for its frequency. That would be 94.5 million waves per second going by any given point in space for that particular radio signal. So that's a little, we'll get in more into this when we get into the physics section of the course, but just wanted to give you a little background on it. 35 milliseconds. Milli means 10 to the minus 3, or 1/1000th of a unit. So 35 milliseconds would be 35 times 10 to the minus 3 seconds. Not proper scientific notation, though. So we have to draw the decimal point in, since it wasn't there already. And then we have to move it one place to the left, which is what makes this number 3.5, which is between 1 and 10. So 3.5 times 10. Now, when we moved the decimal point, we made the first part of the number smaller, so we have to make the minus 3 bigger by 1. And remember, negative numbers, watch out. -2 is actually bigger than -3. So it's -2 seconds. That would be 35 milliseconds. Okay, so we're done with that. Done with that section. Let's see, next we have the sheet that's entitled More Scientific Notation Metric Prefix Practice. So we'll go on to that one. Okay, so the first couple sections of this are similar to what we just did. So the next one, Roman numeral 1, replace the metric prefix with an exponent. And if that's not in proper scientific notation, convert it to proper scientific notation. Okay, so we'll want to do that also. Number 1 is 835 microseconds. 2 is 3.50 centimeters, and 3 is 0.840 megahertz. Again, there's that hertz again, but the mega is the only part you really need to be concerned about here. And let's see, I'm going to continue on with part 2, because that is just change these to scientific notation. There are no prefixes in these 3. Okay, so these will, you can pause the video and work on them for a couple of minutes, and then we'll see what we got when you start up again. Okay, so if you're starting up again, For the first three, we have to look at the prefix and change it to a power of 10. The funny looking U with a tail on the front, remember, is the Greek letter mu, and it corresponds to 10 to the minus 6. So 835 microseconds would be 835 times 10 to the minus 6 seconds. I wrote the decimal point in because I noticed the end of the 5 there looks kind of like a decimal point, so I didn't want you to be confused. Now, this is equivalent to this, but this is kind of an in-between state, which is neither proper scientific notation nor the proper decimal form. So what we can do is change it to scientific notation. The first part of the number has to be between 1 and 10, so we're going to have to move this decimal point 2 places to the left. So that's 8.35 times 10 to some power, and it's -6 to begin with, but we've moved the decimal point 2 places in the direction that makes the first part of the number smaller, so we have to make the 6 bigger by 2. So we count up from -6 to -5 to -4. So 8.35 times 10 to the minus 4 would be the proper scientific notation for 835 microseconds, also using the base unit. Of course, you could also, for proper scientific notation, if the problem didn't say first replace the metric prefix with an exponent, you could just call this 8.35 times 10 to the second power microseconds. So it's 8.35 times 10 to the second is 835. But since we've been told to replace the prefix, we have to do that first. Okay, 3.50 centimeters. Centi is 1/100th, or 10 to the minus 2. So this would be 3.50 times 10 to the minus 2. Whoops, centi is gone now. Meters. And that is proper scientific notation, because the first part is between 1 and 10. We have 0.840 megahertz. Remember, mega is 10 to the 6th. So this would be equivalent to 0.840 times 10 to the 6th hertz. But 0.840 is not between 1 and 10. So we have to move the decimal point 1 place to the right, which gives us 8.40, which is between 1 and 10. Now, moving the decimal point made this part of the number bigger, so we have to make the exponent smaller. So 8.40 times 10 to the 5th hertz would be the proper scientific notation. For the next three, we don't actually have to worry about any prefixes, so we can just go straight for the scientific notation. We have 0.00439. We have to get it to be between 1 and 10, so you move the decimal point 1, 2, 3 places to the right. That's 4.39 times 10. This is a number that's less than 1, so it's going to be a negative exponent. You can also tell that the exponent's going to be negative because you made the number bigger when you move the decimal point. So you have to use a negative exponent to compensate for making the number bigger. And we moved it 3 places, so the power is going to be -3. So there you go, 4.39 times 10 to the -3. 950 meters, the decimal point is implied to be after the 0, but there is no decimal point, so that's why I'm putting it in parentheses. Just, remember, this is going to be a 2-digit number when you write it in scientific notation, because that 0 at the end doesn't count because there was no decimal point originally. 1, 2, moving the decimal 2 places to the left gives us a number that's between 1 and 10. But remember, it's 9.5, not 9.50, because there was no decimal point originally, and that 0 at the end doesn't count. So 9.5 times 10 we moved the decimal point 2 places, and we moved it in the direction that makes the first part of the number smaller. So we use a positive exponent, in this case, meters. Okay, so 9.5 times 10 to the second. You don't actually have to write the plus in front of the 2 if it's a positive exponent. If there's no sign, you assume it's positive. I just wrote it in to be clear, make it obvious. And then we have 25,000 meters. Once again, we have an implied decimal point. So I'm going to put it in parentheses just so I remember that it wasn't there to begin with. And then if we move the decimal to a point where the number is between 1 and 10, we have to move it 1, 2, 3, 4 places to the left. So our number ends up being 2.5. Remember, since there was no decimal point originally, those zeros at the end don't count. So this is really just a 2-digit number from as far as significant figures go. And it's times 10 to the 1, 2, 3, 4 power. Moving the decimal point made the first part of the number smaller, so you use a positive exponent. Also, this is a big number, so it should have a positive exponent. And so, oops, don't forget the units. So 2.5 times 10 to the 4th is the same as 25,000. Okay. Roman number 3 on that page. Is replace the exponent with a metric prefix, which is what we did a couple parts ago. Anyway, we've got some numbers that are in proper scientific notation and some that aren't in this case, but we just want to replace them. But that just means that the power of 10 is already in a position where you can identify a metric prefix with it from among the ones that we saw the other day. It's 4.05 times 10 to the 3rd. Okay, so what we got here is 34.8 times 10 to the minus 1 seconds. If you look at the list of metric prefixes, you remember that 10 to the minus 1 means deci. So this would be 34.8 deciseconds. Or 34.8 ds. For the next one, 4.05 times 10 to the 3rd. Remember, 10 to the 3rd is kilo. So that would be 4.05 kilometers, or 4.05 km. And 585 times 10 to the 6 watts. 10 to the 6th is the prefix mega. And so what we have here is, I don't know why I can't make 5, 585 megawatts. Or 585 capital M, capital W. Okay, so far so good, hopefully. And for part 4, we're supposed to convert to decimal form. Eliminating any metric prefixes along the way. Okay. So I'll write down what we're given, and then you can pause the video and work on it a little bit, and we'll see what you get. (8.5 times 10 to the 7th meters is 10, 11, 8.5 times 10 to the minus 7 meters. And then we have 750 megawatts. And then 9.4 centimeters. 9.40 centimeters. Okay. Now we can go and do some of the, so you can pause the video now, and then when we come back, we can compare results. If you're checking against the answers at the bottom of the page, beware that M is, the number 11, the original answer was wrong. I have the original answer written in here, but I don't remember if that transferred over to the copies you guys get. So yeah, the original number 11 is wrong. Okay, anyway, if you've had a chance to work on these, we can start looking at what we got here. First of all, we got 8.5 times 10 to the 7 meters. There's no prefix here, so we can just go straight for the decimal form. The exponent is positive. That means we're going to be moving the decimal point in the direction that makes the number bigger. You can also recognize that just by the fact that a positive exponent means a big number. Okay, so we move the decimal point to the right because that's what makes the number bigger. 1, 2, 3, 4, 5, 6, 7 times. But I'm going to put the decimal point in parentheses because when we move the decimal point like this, this number was originally written with 2 significant figures. That means you want your answer to have 2 significant figures. You don't want to put a decimal point at the end and imply that all those zeros at the end of the number are significant. Okay, so we end up with a bunch of empty spaces, and so the empty spaces are filled in with zeros. And so that's 1, 2, 3, 4, 5, 6 zeros. And that means 8, 5, 0, 0, 0, 0, 0, 0. And that's it, no decimal point. And there you go. So basically it's 85 million, 8.5 times 10 to the 7th. Here we have 8.5 times 10 to the minus 7, so you have to do pretty much just the opposite of what we did. You have to move the decimal point 7 spaces, but to the left instead of to the right. So 1, 2, 3, 4, 5, 6, 7. This time you can write the decimal point in because remember, zeros at the beginning of a number never count whether there's a decimal point or not. Doesn't matter. And so this number will still be 2 significant figures no matter how many zeros you put in front of it. So that's 1, 2, 3, 4, 5, 6. 6 zeros. And there you go. For 750 megawatts, this has a metric prefix, so we would want to replace that with 10 to the 6th first, and then we can change to the decimal form. So this is 750 times 10 to the 6th watts. And for before changing it to scientific notation, or sorry, to decimal form, we look at where the decimal point was originally, which is understood. It's not actually written there, so I'm going to put it in parentheses. And we have to move 6 places in the direction that makes the number bigger, which is to the right. So 1, 2, 3, 4, 5, 6. So that's where the new decimal point goes. But again, since we're talking about the end of the number here, you don't actually want to write that decimal point in, or all those zeros count. And we only want a 3-digit number. Mm-hmm. Okay, so 750 followed by 6 zeros. Watts. With no decimal point, actually, this is one of the disadvantages to writing numbers in the decimal form, because there's actually no way to write this number in the decimal form so that it has 3 significant, or sorry, the original number only had 2 significant figures. Sorry. Yeah, there really is no way to write it so that it has 3 significant figures. But that's okay, because without a decimal point, it has 2 significant figures. With a decimal point at the end, it would have a whole lot of significant figures. So actually, it did work out all right. And then next, we have 9.40 centimeters. 9 means 10 to the minus 2. So our first step would be to change this to 9.40 times 10 to the minus 2 meters. And then we can move the decimal point 2 spaces in the direction that makes the number smaller. Fill in the empty space with a 0, and we get 0.094 meters. And that would be the proper decimal form for that number. Okay, so that's that page. Next, we actually start in on unit conversions. That's going to take quite a bit of time, because unit conversions, for the most part, they're not all that difficult, but they are a very important part of this class and really any science class. So we're going to want to spend a little bit of time on them. I see that we're almost up to 30 minutes now anyway, so I'm going to stop this segment of the video now, and we'll start with the unit conversions in the next segment. Okay, I'll see you.